Welcome back everyone on the second video of the sine rule, and in this one we're going to take a look at a few example problems to make sure that we really understand how to not only apply but also when to use and how to use this property. Let's go ahead and start right now. Okay. So in our first example, we're given a triangle of QRS where QR is 15, SR is 6.5, and the angle of S is 125. Now we want to find Q, the angle of Q, capital Q. And we want to give our answers correct at three significant figures. Here's a nice reminder of what our sine rule is. Always a good idea to write that. Now, first things first is I'm going to draw a triangle diagram. Always a good idea. Draw a non-right triangle, and I'm going to I'll put Q up here, put R down here, put S down here. Because I know that S is 125. I know that that's my obtuse angle, so that's where it's a good place to put that. I don't know what Q is. That's really what I want to find out here. And I know that QR, which is the opposite of S, and remember, in our last example, we would have had a little s right there is equal to 15. But it's also correct to say that the side of QR, which is the opposite of S. So QR and S are the same things because they're just referring to the same exact length. And SR is going to be the opposite of Q. That'll be little q, and that would be 6.5. So let's take a look at what we have here. We want to know the angle of Q. So if we want to know the angle of Q, well, we know that we have the corresponding side, and we know that we have the angle of S with the corresponding side. So what I can do is follow this property right here, and even though it's not A or B, the principle is still the same. I am taking one side and its corresponding angle and creating that ratio and equating it to another one and then solving for one unknown. So what is that going to look like here? Well, S is just going to be 15, and then the sine of S is going to be the sine of 125 degrees. And I'm going to equate that to 6.5 all over the sine of Q, and I don't know what Q is. Now, you could rearrange this. You could use Nsolve. There's many different ways to do this. If you wanted to do it by hand, you would move that sine of Q over, and that would give you 6.5 sine of 125 all over 15. So Q would be equal to the inverse sine of 6.5 times the sine of 125 all over 15. Therefore, Q would give us an angle measurement of 20.8 degrees if you look into your calculator. You can use that. If you have the Ti-Nspire, you could, of course, just put this as an Nsolve. Or not that, sorry. This one as an Nsolve. Actually, I guess that one too would work. But either way, you can do it manually. You can do it in the calculator. As long as you're putting in the right inputs correctly and solving for what's appropriate, you'll get the right answer. Now let's take a look at problem number 2. So we have a ship on a bearing of 120 degrees from port A and a 42 degrees from port B. The distance between port A and B is 15.2 miles. Find the distance between the ship and each port. This problem is kind enough to already give us that information. And if you forget what a bearing is an angle that is measured clockwise from the north-south line. So here we have north. This is the north-south line. So that 120 degree bearing is that clockwise angle from that north line, that straight up and down line. So let's find the distance between the ship and each respective port. So if we're trying to find the distance between the ship and each port, so remember the ship is S right here. So we want to figure out how far it is from A, how far it is from B, and yeah, let's just find that out. So here's the thing, is that when you're looking at this, it's kind of difficult to determine where to start because you're looking at this and you're thinking, okay, I have one angle here. Oops. I have one angle here. I have an angle here, and I'm not exactly quite sure where everything else is going to come from. So what's important to realize here is that, like I said, the bearing is the angle measured clockwise from the north-south line. So if you think about a north-south line, that is straight up and down, meaning that whatever this is must be supplementary, meaning adding up to 180 degrees with this angle right here. So 120 plus what equals 180? Well, that's just going to be 60 degrees right there. And then if this is 60 degrees and this is 42 degrees, well, I can subtract that sum from 180 and get my other angle. And in this case, it would be 78 degrees there. Now, I now have 3 angles and I have a corresponding side. This actually makes it a whole lot easier because now that I know that with my sine rule, I can figure out this missing distance as well as this missing distance. So let's go ahead and solve this one by one. So let's go ahead and say I want to solve for, oh, I don't know, I'll call this little b. Let's say I want to find that distance. Okay, so what I would do is I would have that distance be all over the sine of 42 degrees. And that is going to be equal to, again, I don't actually know what this length is yet, meaning that this 60 is kind of irrelevant for this problem. I'm sorry, for this step of the problem. I have to use 15.2 and 78 because those are the corresponding ones. So let me put in 15.2 all over the sine of 78 degrees. B is equal to 15.2 all over the sine of 78, not 7.8. Extend this out a little bit so I can write sine of 42 degrees there. Pop that into your calculator and you're going to get an answer of, to 3 significant figures, 10.4 miles. All right, so there's B. That's one of them. So I can go ahead over here. Once this works, which it finally does, 10.4. Okay, so now that I have those measurements, solving for A actually becomes slightly open-ended. I could use a lot of different ones, but I'll go ahead and I'll keep 15.2 here. So I know that I have 15.2 all over the sine of 78 degrees. And I'm going to equate that to, well, I need the sine of 60 all over whatever SB is. Let's call this little a. Okay, and it's important to note that when I said that this was a little bit more open-ended, what I meant was this right here. That was weird. When I said this problem was slightly open-ended, I was talking about this figure right here, because you could use 15.2 and sine of 78, because they're opposites. You could also use 42 and then 10.4. I personally would highly, highly encourage you to use 15.2 over sine of 78. And the reason is because 15.2 was directly given to us by the problem, versus when we had 10.4, we introduced some rounding in order to get to 3 significant figures. And what that means is that if you're using an approximate answer, it means that this one is more likely to have a wider margin of error when used as a calculation. So if you use 15.2, you're more likely to get it closer to that value because it's given to you directly by the problem. So if I want to go ahead and solve for this, then I would have the sine of 60 times 15.2 all over the sine of 78 degrees is equal to A, meaning that my side A is going to have a length of 13.5 miles to 3 significant figures. So I went ahead and I found the distance from each port to the ship just by using my sine rule a few different times. The only thing that was a little bit trickier when we introduced this was that we had to get this interior angle into the triangle in order for us to get the sine rule to work for us. Because again, we were given one angle and one side, and we were able to determine what this angle was by recognizing that this had to be a supplementary angle to 120 degrees. Okay, I hope that helped out. And in our next videos, we'll be taking a look at the cosine rule, yet another way for us to solve for non-right angled triangles. But don't worry, as long as you have the formula and you know how to use it, you'll get those problems right every time. Take care, and I'll see you all in the next video.